Foundry applications, of course, there are many. It can go beyond data, but what we found that if you want to connect very quickly, then just go with chemical composition plus type of data. But it's applicable to a variety of data. In, say, gravity die casting or pressure die casting, the chemistry data is different, but the process data could be like design of experiment style. But then we can accommodate both data sets to create an impact. In investment casting and sand casting or steel making, the process data also has got a lot of variability. Probably in pressure die casting, once you set that machine on a particular temperature, it will consistently make that temperature. But still, here and also in sand casting, methoding design is quite important, and you can quantify those design characteristics and put into domain. Can be used into design and development stage of new components, because that's the time you're actually doing lots of design of experiments and lots of trials for different settings. Now that data can be reused to develop generic knowledge, which can be then used for new components in trying to minimize experiments on that component. But at the same time, you can take feedback from those components which have gone into production stage and where the process engineers have tweaked that process. So you need to build bridge between the design office and the production office, and of course the supplier as well, if you're working with the supplier to improve quality. So that whenever you have new component, you get feedback from the production stage as well as the experiments. So none of the experiments are lost. When we were talking with another foundry, and they said that, okay, in the last 2-3 years, we almost done over hundreds of design of experiments to develop our new products. Now, if that is just data sitting on somebody's Excel file, it will be lost. And then you come back to drawing board after 5 years. Now, what we need to do is compile those case studies into this format so that this bridge between design office and the production office can be bridged. I want to be sort of not specific about which alloy we use, but in this case, toughness and strength, these are the conflicting parameters, and how do we come up with the best compromised chemistry? And we will see that with very few observations. Shrinkage defect with variety of sand plus chemical composition is a routine thing. That's the first thing you can do straight away, because that data is readily available. But we can go a step further and then convert operator names with their attributes. Skill set, we can have attributes for design data as, for example, number of cavities, average or section thickness gradient, and you can get some geometrical packages to give you that information. Perhaps you can go into sieve analysis, friability, detail analysis to address this inclusion problem, because you can't do design of experiments. Of course, the cleanliness and the basic thing that come to your mind, we assume, are already implemented, because that's why you are into this 4 to 5% range and not into 20 to 30% range. Shell making, again, the point here is that in one of the sub-processes, for example, of course, in inclusion, the problem always is in shell room, as far as investment casting process is concerned. But what we are saying, that the output of, say, shell room, for example, shell strength, permeability, or weight, is an output of shell, but that becomes an input parameter to casting process. Mold hardness could be an output of mold making process, but it's an input parameter to casting process. You need to manage that, and that's how you connect data from those. But this becomes really advanced analysis. The first step, we start with whatever you got. This particular example, which we are discussing with shrinkage data and nickel-based alloy, you might have only data on to, say, 20, 30, 40 heats. Then you got a sort of difference in rejection rate. And then you can see that rejection across the components, because you use the same furnace for 5 or 6 different families of components. So you can see the variation across components, maybe pick up some components which are sensitive, and then you look at its methoding design. But at the same time, you want to start tweaking chemistry. You don't want to wait for 100 observations to build up. So you can start analyzing data through penetrative matrices. Even the design of experiment data, where you've got only 20 observations. The philosophy is useful, and the trend are quite meaningful. Jobbing foundry. One of the feedback that we had, that we don't repeat our job again. So when I cast it, why should I bother? Because I'm not going to do that data for next 5 years. Yes, correct. But then you don't tweak your process for every component. You have same chemistry. If you're going to have same process parameters, then you can reuse that because it belongs to a family of components. And therefore that data can be shared. You need to quantify these product characteristics so that the software or data visualization tool will recognize the variation within the family. For example, this particular one has a sharp change between section thickness, or the variation in section thickness, variation in the parting line, the cores, undercuts. You need to develop some criteria to quantify those, and then group that data, group those similar components to analyze this information. So when you get a new component, you'll say it belongs to this family, and therefore that data can be reused and shared. You need to think how you can incorporate those methodding results. Because so much information is already available, and how we can reuse that, because our mind does that automatically. So we just have to ask ourselves and code that.